As promised, we will go over the proof of the basic density bounds because the proof illustrates some of the common tricks and techniques in metric geometry and the effectiveness of covering theorems. A quick recall that the densities were defined for all real dimensions for all subsets at points that are not necessarily in the set itself. The upper density definition you see here and the lower density is defined similarly where we replace limit supremum with limit infimum. The motivation and where they come from have been discussed in previous videos, so please do check them out if you haven't. And also some surprising deep results from geometric measure theory were discussed in the follow-up videos. The theorem of interest that we will be proving today, at least part 1 of it, because part 2 is similar and I'll leave as an exercise, claims that the upper density is always between 1 and 2 to negative s, always being a measure theoretic sense that it's at almost every point of the set E. And if the set is measurable, the upper density is 0 outside the set, which shouldn't be too surprising because, well, we are outside the set. Okay, the proof, again, of only part 1, let's begin by looking at the lower estimate of 2 to negative s. So the bad set of points where this is violated, x in E, where this upper density of E at x is less than 2 to negative s. Okay, call it F. It's a subset of E where the estimate that we want fails. So what this means is that F is those points in E where limit supremum is less than 2 to negative s. Well, what are the numbers that are less than 2 to negative s? They are, so a number being less than 2 to negative s means that it's less than some I over 1 plus I, like 90% of 2 to negative s for some I. So if you're strictly less than a number, you're strictly less than a fraction of that number, provided that we allow arbitrarily large fractions close to 1. And this trick of breaking up into countable union is a very common technique in measure theory and geometric measure theory of proving that the estimates for sets. So we will break F into pieces and then prove that the measure of each set is 0. Let's also emphasize that all we need to show is that this set has measure 0, which would mean that it's almost everywhere the opposite inequality holds, which is the lower estimate that we want. Okay, to show that hs of f is 0, we will decompose f into pieces and then prove that those pieces are 0. And the reason such a trick works is that we get a strict inequalities rather than just borderline inequalities. That's the whole idea. Okay, but what is when is the upper density less than some number? Well, this is lim supremum as r goes to 0, and for lim supremum to be smaller than A quantity means that for all small values of r, okay, so that means there exists some delta positive such that for all small values of r, this fraction in the definition of upper density, hs of E intersection with bxr divided by omega sr to power s is strictly less than I over 1 plus I 2 to negative s. Okay, so lim sup being less than a number, that means for all small radii this happens. This may fail for like r bigger than 25, so we still need to look at only small radii. But I claim that this, instead of looking at a continuum of such delta, we can only consider a discrete one. So this will be I going 1 to infinity, and then we can take 1 over j's for delta. So then for different x, this may happen sooner or later. Some x will require smaller delta, some x will require, will not be as strict, but all of them will be captured by this. So x is in E such that 1 over j is sufficient. So that will mean that h of s E intersection with bxr, nothing new here, just the definition, is less than I over 1 plus I 2 to negative s for all radii less than 1 over j. Now here, this is not super difficult, but you can combine them into just one union. You can take I equal to j. This needs a little bit of thinking. This is because when I goes up, this actually becomes an easier estimate to have. So if this holds for some I, it will hold for the future I as well. And that means once you make this delta, this j, to work for some x, you can chase with I to get the to get it larger than larger than j. So what I'm saying is that it is not that these two conditions, this inequality and this one, are working against each other. They are actually working together. That's why you can combine them into saying that, well, let it happen at the same rate, so that hs of E intersection with bxr divided by omega s r to s less than k 1 plus k 2 to negative s for all r that is less than 1 over k. So I leave that confirmation for you. Okay, the last ones, these objects we have, we call them fk. So fk is the set in the interior. Okay, so we succeeded in writing f as such a union, a countable union. So it suffices to prove that hs of fk is 0. Then by subadditivity, it will follow that hs of f itself is 0. By the way, I am also following the proof from Mattila's book. This is chapter 6. My notation is a bit different. Mattila calls this bad set B rather than F, but then I didn't like it because I always keep thinking that B means a ball. Okay, how is this going to be achieved? Okay. For simplicity, let's write T to be K over 1 plus K. It's a number less than 1. And let epsilon positive be arbitrary. Okay, by definition of Hausdorff measure and Hausdorff content, so remember that this HS is defined through HS deltas and then letting delta go to 0. We have, so here I'm going to take delta to be equal to 1 over k. So how do you estimate the HS delta of a set? By finding coverings. Okay, by definition of this, we have a covering of the set Fk is a subset of some countable union of sets, maybe finite, so let's not write infinity, just some I, but at most countable, such that, well, it's a delta covering, so diameter of AI are less than 1 over k, and okay, so HS of this Fk plus epsilon, which is at least HS delta, well here delta is 1 over k again, of Fk plus epsilon will be larger than, so because this HS delta is a supremum, sorry, is an infimum, we have found one particular covering these AIs, so that, well, how do you define HS? So this is WS, diameter of the coverings divided by 2 to power S. Okay, so we can find a covering with this property, and there's nothing special about here if you recall the definition of Hausdorff measure and content. We can require, without loss of generality, that for every AI intersection with this Fk is non-empty. So for the rest of this proof, we kind of have fixed k, and the indexing now is I, which is the covering of Fk. We could even drop this k from notation for simplicity. Well, why can we do this one? Because, well, if you have a covering of Fk, and if some AI happens to not intersect Fk, that means that set is not even needed to cover it, and we can completely drop it from the list of sets that covers. So this is always true, that you can require that every set does indeed contribute to the covering. But here, why is this important? Because we want to pick points from this intersection, and we will use that to recover our estimates, to bring in our estimates. So remember that we have defined Fk with some certain properties, but yet we are going to use those estimates. So this will be the center of the balls, this xi, and the radius of the ball will be the diameter of the set AI. So for every I, fix some point and some radius. Then what happens is that this Fk intersection with AI is a subset. Well, Fk is a subset of F, which in turn is the subset of E. And AI, well, you have a point in AI, and then you have the radius equal to the diameter. So if I take this ball at xi with this radius, So its radius is equal to the diameter. It contains even the farthest points from AI. So that means this set is in subset of that, and this is subset of that. So this intersection is a subset of that intersection. And these may seem kind of technical, but the reason for why we're doing this is obvious, because now this looks like a familiar thing. This is just the numerator in the definition of upper density, and that's how we bring in the characterizing definition of Fk. So let's just apply every estimate that we've had. So Hs of Fk will be less than or equal to, so this is just subadditivity, Fk is covered by AIs, so this will be Fk intersection with AI. This is just subadditivity. It doesn't even require measurability or anything. Remember, we haven't even assumed that E or Fk are measurable or not. But then now we have this thing. If we have a subset, then the measure goes only up. So this is E intersection with Bxi Ri. But guess what? Xi belongs to this bad set Fk where the density was larger, and Ri is less than 1 over k. So an Fk were exactly those points Xi for which the fraction was less than 2 to negative s for all radii less than 1 over k. So it fits all the criteria, so that this will be less than k over k plus 1, which we call t. And then this will be, well, the denominator, and then Ri to power s times 2 to negative s. Okay, so t times 2 to negative s. But this is nothing other than t, summation over I, omega s. What is our I? This is diameter of AI. And let's bring this 2 inside, then the whole thing to power s. But how had we chosen AI? Where did AI come from? AI were so chosen that this summation was less than Hs Fk plus epsilon. Wow. We started with Hs of Fk and we ended with that. But epsilon is arbitrary, so we can take it to be 0. So let epsilon go to be 0, because this is true estimate no matter what epsilon. To recover that Hs of Fk is less than or equal to T Hs of Fk. But T is strictly less than 1. So Hs of Fk, okay, when can we have this although T is strictly less than 1? Either this Hs of Fk is infinity, or if it's 0. But it's not infinity. Remember that Hs of Fk is less than Hs of all of F. That is less than Hs of all of E, but that by assumption was finite. So the only case is 0. And that is precisely what we wanted. This is for arbitrary k, and F is union of Fk. So we have proven that Hs of F is 0. These proofs at first may seem kind of magical out of nowhere, but in reality you're just following the estimates. The estimates show you the next step. There are no alternative ways to proceed, so you just apply the definition. But again, my motivation for showing these proofs was in case you haven't seen already, some of the common tricks in dealing with geometric measure theory arguments. For example, this decomposition of f into these steps helped us with bringing in a strict t. So if you had proven without this trick, you would just have t equal 1 here, which was of no use. So remember this trick, that when you have a strict inequality defining a set, you can avoid the borderline by bringing in this buffer zone. That usually is sufficient to make stronger claims than you could otherwise, which leads to stuff we just saw. Okay, so the set of bad points where the density, so remember this f was the set of bad points where the density was strictly less than 2 to negative s, has 0 hs. That means almost every hs, almost every point will be this way. Okay, so let me prove the upper estimate, and the part 2 again will be left as an exercise because the proof will be similar. This time it will be obvious why now I'm looking at sets like this one. So let t be some number strictly bigger than 1, and define, this time the bad set will be, we want to show density is less than 1, so let's look at those points in E where upper density of E at x is strictly bigger than t. If we show hs of f is 0, which implies for every t, then we're done, because it will say that you never have a strictly bigger than 1 density almost everywhere. Okay, for important reasons, we have to add this, bring in this argument that we have actually used before, proven before. So we can assume that E is Borel. Okay, where does this come from? The proof of this is as follows. Since Hs is Borel regular, and this is something I covered in the Hausdorff measures playlist. There is a separate video just dedicated to this and its proof. Okay, let me clarify what this means. Hs is Borel regular. That means there exists some larger E tilde that is Borel, and Hs of E tilde equals Hs of E. So you enlarge your set, but you don't increase the Hausdorff S measure. And the enlarged set is Borel. And notice that the upper densities of E tilde at any point are at least as much as the upper densities of E at that, simply because E is a subset of E tilde. So if we prove the claim that upper density, that this upper density of E tilde x is less than or equal to 1 almost everywhere, then we have proven the same for E. So that's why we can assume without loss of generality from the beginning that E is Borel. So instead of working with E tilde, you just basically rename E tilde back to E. Okay, So again, fix some epsilon positive. And let this measure be HS restricted to E. So what is this measure? This is a notation for the following measure. The measure of any X subset is just HS. First you intersect with E, that set, and then you apply that. This is just the meaning of that notation. Then mu is a Borel measure. This is where we're using this argument to replace E with a Borel set, so that we can just say this measure is Borel because it's so super important. By being a Borel measure, we can bring in this one. So there exists some U that is open and contains the set F. So now we are back to this set F, the new bad set that we have. So for every set, that is the property of Borel measures, that for every set F, there is some open set containing it, such that the measure is actually pretty close. So that means we can estimate the measure of any set by open sets larger than that. So U is bigger than F, but its measure is not much bigger than that of F. So up to this epsilon. So for every epsilon, we have an open set which estimates F in measure. But let's translate this. What is that? Mu. Mu of U is nothing other than U intersected with E. And this will be HS of F intersected with E. But F is a subset of E, so we just don't need to intersect. So that is this. Okay, if X is in F, what does then that mean? Then upper density of E at X is bigger than T. This is a lim sup. Lim sup being bigger than T, that means for every delta positive, that means, okay, at arbitrarily small scales, there are radii such that HS of E intersected with BXR divided by omega SR to S is bigger than T. This is not for all R, remember, this is for some R. Lim sup bigger means you keep hitting larger than that value, but you could also be going down. So this could, the set of R where this happens could be a discrete set rather than the whole interval. All we can say when lim sup is bigger is that you keep coming back to large value. No matter how small delta you set, still there are smaller than that radii where this happens. So we can also, because we can choose this radii arbitrarily small, we also can remain within U. So here's some set F, and here's some open U containing it. So at every point here, because it's an open set, there is some radii which remain inside U. So we can do both of these things together, that there are arbitrarily small radii R such that, let's call this star, star holds, and at the same time this ball of radius x and r is contained inside the open set U. This follows from openness of the set. I must say that I also keep them less than delta over 2. Again, because arbitrarily small exists, we can arrange for this. Now here comes a covering theorem, but this is for fine coverings. I haven't discussed this in Young measures, but this is a bit different, the situation here, because for the set F, at every point there is some, not just one, but a whole bunch of arbitrarily small radii. So every point is covered, and you can find a ball of whatever small radius you wish while keeping this desired property. And that is a better covering than just having a union of balls. This is, you can cover them at any scale you wish. And when you have such a collection of balls covering a set, you can do better than the 5R covering lemma. And the better than covering 5R covering lemma is the following. There exists some disjoint balls BI such that, okay, they are disjoint just in like a Vitali covering, such that they still cover your set. So these were covering F. So there were many balls covering F, but now we have chosen a disjoint union of them. I mean, only a countable collection of them that are mutually disjoint. There could be only finitely many. This would be empty in the 5R covering lemma, but this time it's not empty. That means it doesn't cover F, but it effectively does that. So up to a measure 0 it covers. So these balls, we pay a price. We don't expand them 5 times. That's a big achievement. On the other hand, we don't really cover it as a set, but up to measure we do. And usually this is just sufficient enough. The fact that we don't have to multiply by 5 the radii of the balls is significant and very important in many applications. I also must emphasize that this is different from the Besikovich's theorem. Here you genuinely cover by one collection of balls. Okay, so let's put things together. What happened? This time around, to prove that almost everywhere the density will be less than 1, less than or equal to 1, we again started to look at the set of bad points where it's strictly bigger than 1. And again, by discretizing, we can look at 1 plus epsilons. Okay, this is the set of bad points. For technical reasons, we assume that the set E we started with is actually a Borel set, so that we can find an open set containing this bad set, this U containing the bad set, but with measure not too far different from that. And then by the definition of upper density, at every point in X, there are arbitrarily small radii, so that this fraction is bigger than t, and you never leave the open set U. And finally, for the setting, we apply this fine covering lemma. So what can we do with this collection of balls, the set U, to prove that F must have 0 measure? Okay, here is the answer. We want to estimate HS of the bad set F. So let's add this epsilon. This will be bigger than HS of E intersection with U. This is what we had done in choice of the set U. Right, that is that part. But then this is less than IHS of E intersection with BI, this disjoint collection of balls. This one is true because BI are disjoint, and then subadditivity of HS. But then BI were chosen with their special radii so that this star inequality holds, which then can be written as it's bigger than T omega S Ri to power S over I. So let me double check this. T times, yes, star means this measure is bigger than T times Ws Ri to power S. Okay, Ri are less than delta over 2. That means these balls, diameter of these balls is less than delta. So this one is an upper estimate for the delta S delta content of the set. Okay, so BIs, so these are BIs, therefore this will be union of BIs. Okay, so I can make it a smaller set by intersecting with E. Okay, so I'm using this union of BI as a covering of this set, and that's a delta covering, so this summation is so these are, remember, diameter of BI divided by 2 is just Ri, then to power S. So that's definition of the Hausdorff content. Okay, the point now here, oh, okay, sorry. So I don't want to go this far up. I became too generous. So the bad set F intersection with that. Okay, these balls, right. The union of balls, of course, cover F again, because for every point we have chosen one. Okay, but this one is nothing other than T HS delta of all of F. Okay, this one is not trivial. This is because of this one here. So the deficit, the difference between having intersected with this versus not intersecting with it. So this is apparently a smaller set than this. Set theoretically, this is smaller than that. But the deficit has 0 HS measure. And remember that HS of something is 0 means that HS delta of that thing is 0, simply because this is less than that. But more is true, the opposite is also true. Okay, finally now we are here. Again, we started with some HS of some set, and we basically ended with that. And that can be made precise because delta is arbitrary, and so is epsilon. So if we let them go to 0, I don't think the order matters here, but we can double check. To recover that HS of F is strictly bigger than T times HS of F. Again, T is strictly bigger than 1, which forces that HS of F is actually 0. And that ends part 1 of the theorem. Part 2 is an exercise And let me give you a hint that for part 2, only Vitali 5R covering suffices. So there the estimates are in the right direction, so that dilating the balls does not matter. And also you want to prove something is 0, which means multiplying by a power of 5 and then proving it's 0 doesn't matter. In these ones that we showed, we were working with positive numbers 1 and 2 to negative s, so we couldn't freely allow multiplication by power of 5. But hopefully this was worth it, and you picked up some tricks along the way. The proof is in section 6 of Mattila with some notational difference, especially with the difference that Mattila's, as is the common practice in fractal geometry, does not apply this omega s in the definition of Hausdorff measures. Therefore, there are small differences between what I wrote and what is in the book, but the proof is essentially the same. Okay, please comment your observations and whether you had seen this proof, whether you have seen other maybe simpler proofs of this result, and see you in future video. Please also keep subscribing, because that's what tells me you like the content and want more. Thank you and have a good one.